The Alert Research Center's focus on detecting explosive-related threats is helping first responders become aware of explosive materials that could be used for malicious reasons. This is a challenge that is much more difficult than it seems. First, we need to understand the basic properties of atoms and molecules.
Everything around us is made up of atoms. They are the smallest form of matter capable of maintaining their characteristics and properties. An atom is made up of three parts: protons, neutrons, and electrons. The protons and neutrons are found in the middle of the atom, creating an atomic structure called the nucleus, while the electrons orbit around the nucleus. The electrons' orbits can simply be referred to as shells, the first of which holds 2 electrons, and the rest hold 8. A shell is considered full when it has 8 electrons. Once a shell is full, any additional electrons will then occupy the next highest shell. The outermost shell is known as the valence shell, and is the shell that contains the electrons that will be used when bonding with another atom. So, if the electrons are orbiting around the nucleus, what keeps them from just flying away? Have you ever heard of the saying, opposites attract? Well, in the case of atoms, this is especially true. Each particle in an atom has its own charge. Protons have a positive charge, neutrons have a neutral charge or no charge at all, and electrons have a negative charge. So the protons and the electrons are attracted to one another because opposite charges attract each other, and that's why the electrons don't just fly away. A whole atom can have an overall charge as well. That charge is based on the number of protons and electrons in the atom. So let's take carbon for instance. According to the periodic table, carbon has an atomic number of 6. That means that carbon has 6 protons. So for each proton, we will add 1 to the atom's charge. This also means that there are 6 neutrons in the nucleus. Now, in order to maintain a neutral charge, we have to bring that charge number back down to 0 by subtracting 1 for each electron. This also indicates that carbon initially has 6 electrons. When the number of protons and electrons are balanced, the atom's charge is neutral. If we were to add an electron, the atom's overall charge would now be -1 because there are 7 electrons and only 6 protons. Now let's say we subtract 2 electrons, meaning there are 5 in the atom. The carbon atom's overall charge would now be +1 because there's 1 more proton than there are electrons. Whenever we add or subtract electrons to make the atom's charge anything other than neutral, we create an ion. If it is positively charged, it is called a cation. If negatively charged, an anion. What would happen if we changed the number of protons in the atom? Well, we wouldn't have the same atom at all. This would change the element itself. Protons are the most important part of the atom. That would make an atom an element. Now that we know what makes up an atom, we have to know what motivates an atom. What does it want? Well, the answer is not all that impressive. All an atom wants is to be full. And an atom becomes full when it has 8 electrons in its valence shell. The only exception to this rule are hydrogen and helium, which only want to have 2 electrons in their valence shells. So the question is, how do atoms come up with the electrons they need to become full? The answer? They share or bond with another atom. When this happens, 2 or more atoms come together and bond, creating what is called a chemical reaction. As a whole, they are called a molecule. Such an example of a molecule is CO2, or carbon dioxide, which we breathe out every time we exhale. Let's take a closer look at how this works. The carbon atom has 4 electrons in its valence shell and wants to gain 4 more for that total of 8. Each of the oxygen atoms have 6 electrons in their valence shells and want to be full and balanced too. So what do? They share electrons. The carbon atom will share 2 electrons with each of the oxygen atoms, which in turn share 2 electrons as well. So everybody in this situation is full and balanced. How atoms share or transfer electrons is central to the relationship or bonds between atoms. When atoms like oxygen and carbon get together and share electrons, it is called a covalent bond. How they share those electrons can be used to describe the type of bond they share. When one atom hogs the shared electrons, it is called a polar covalent bond because the electrons are spending more time in one part of the molecule, giving that part of the molecule a more negative charge, while the part of the molecule with less electrons has a more positive charge, meaning there's polarity in the molecule. Because electrons are always on the move, that polarity only lasts a moment, and that moment is called a dipolar moment. If the atoms are able to share the electrons evenly, it is called a non-polar covalent bond, meaning no polarity and no dipolar moments. Ionic bonds, on the other hand, are when two oppositely charged atoms come together and give each other electrons. Say, for example, one atom lost an electron, meaning it has a more positive charge, while another atom gained an electron, meaning it has a more negative charge. When the two atoms come together, the negatively charged atom will give an electron to the positively charged atom. That's a lot to take in, but now that we know more about how atoms work and how molecules are created, we can begin to identify them. By using each molecule's characteristics, we can begin to detect what specific chemical it is. One of the most common ways to identify molecules is by examining its mass and its charge. Mass spectrometers use these two characteristics to identify molecules. First, a sample of the molecule is vaporized by rapidly heating it up. Then it's ionized by shooting electrons at it, in this case creating cations. Next, it's shot through a magnetic field, which alters the path of the molecules, causing them to hit different parts of the sensor. This happens because, as the molecules pass through the magnetic field, each molecule's mass and charge is what determines how much of the molecule's trajectory will be affected by the magnet's force. The more mass a molecule has, or the less charge a molecule has, the less the trajectory of the molecule will be affected. The ability to spread molecules out by mass and charge allows us to see the spectrum of molecules in a given sample by recording how many of each type of molecule have hit the different areas of the sensor. Another way mass is used to detect a particular molecule is utilizing a nanocantilever. A nanocantilever can be described as a very, very small diving board that vibrates or bounces up and down. This diving board has specific receptors on its end that are used to attract whatever chemical is trying to be detected. Once the chemical of interest sticks to the diving board, it adds mass to the diving board itself, which changes the amplitude or frequency at which the nanocantilever is moving. These changes can be measured by the device and compared to the expected result for the chemical of interest. Instead of identifying molecules by mass, we can identify by the way they react to radiation, or how their bonds react to radiation. One way of measuring the increased excitement of molecules is infrared spectroscopy. Infrared radiation waves are sent through the sample of the chemical in question. When the frequency of the infrared light matches that of the molecule, part of it will be absorbed, so the light that gets through to the receptor at the other end will change. This change in the infrared can be measured very precisely and be used to identify the presence of a chemical. Adding a trigger chemical to the chemical in question is also a way to identify what chemical you have. This is identification by chemical reaction. Perhaps the trigger chemical is created to change color depending on what chemical you're sampling. For instance, the markers used to detect counterfeit bills. There also might be some specific reaction that you're looking for to distinguish which chemical you have.
ALERT uses these techniques and many others to detect and identify explosive chemicals in order to stop explosives from harming the general public. By detecting explosives earlier and more efficiently, ALERT's research can help first responders and security organizations by notifying them of the existence of explosives. More information about ALERT's research in characterization and detection of explosives can be seen in the next video, ALERT 101, Explosives Detection and Characterization.